Good morning. Hopefully you remember our continuity lesson and the formal definition. This video is just some examples about how to use that formal definition. See if I can get things to move here. Okay, we're not going to worry about the warm-up, but if you're not in class today, you can go ahead and check that out. Make sure you can do both those warm-ups. By the way, up here, this is supposed to be jumbo jet. Haha. Okay. So hopefully you can use the formal definition of continuity, or hopefully you remember. We'll review that on the next slide. And we're going to use that formal definition to decide when a function is or is not continuous at a point. The next lesson, the next video, we're going to make sure we can understand and use the intermediate value theorem, which relies on continuity, but that's not today. As a reminder, hey, if you're in calculus, you should always be checking continuity all year for all functions without being reminded, at least eventually. A lot of things we do, you do, are going to rely on the idea of continuity, or you'll have to watch out for that. So this is the image I want you to keep in mind. So if we're talking about a function being continuous at a point, the left-hand limit and the right-hand limit not only are equal, but equal the y value in the center. Like there's no hole, there's nothing missing, everything's pointing at the same spot, and that's for all points. So we can also combine that into, instead of two one-sided limits, that two-sided limit, x approaches some number of some function, is equal to the y value of that function. Okay, so here we go. So we don't want to always have to do numeric limits. If you have the limit as x approaches 2 of x cubed, and you know, hey, x cubed is a polynomial, so x cubed is continuous, well, that allows us to not do a limit. We're going to use this alternative definition, the kind of two-sided thing. Instead of us doing the limit, since we know the continuity piece, what we know is the limit as x approaches that number 2 from both sides of x cubed is just going to be equal to that y value. So 2 substituted into that x cubed. So the limit as x approaches 2 of x cubed is simply 8. And that's even more powerful than what we were talking about last week, just kind of imagining that numbers near 2 cubed are going to be equal to 8, because this is kind of more proving it, almost like a numeric limit. So likewise, we can do that here. So even though sine's not a polynomial, if you know sine is continuous, and you should, you can imagine the graph of sine. Why am I getting an eraser? Right? Graph of sine, something like that. Well, sine of x is continuous. And the nice part here is, sine of 3.9, sine of 4.1, those are numbers, but they're not memorized values. You'd have to use a calculator, use a computer to get those values to actually do a numeric limit. So if sine of x is continuous, what do we know? We know that the limit as x approaches 4 of sine of x is just going to be equal to sine with 4 substituted inside. We're relying on this formal definition. Hey, that limit's just going to be equal to the y value. We're starting off with, hey, we know this function's continuous instead of trying to prove this function's continuous. All right, so sometimes you need to show a function's not continuous, and hopefully you know, let's see, what does 1 over x look like? Oop, I keep hitting a button here on my stylus. So there's 1 over x. I'm not used to this new computer. And f is not continuous at x equals 0. So let's see. I want it to be that the limit as x approaches 0 of f of x should be equal to f of 0. Well, we know that's not true. F is discontinuous at x equals 0, so how can we break this? Well, f of 0 is the y value of f at 0. And, it's pretty easy to tell. F has no y value at 0, so we could say, hey, these are not equal because f of 0 is undefined. We also could have said that maybe the limit, so we'll say or, the limit as x approaches 0 on the left-hand side of f of x does not exist. And, while that limit is kind of negative infinity, a limit is a y value that the function is approaching, as in this case, x approaches 0 on the left. And those y values aren't approaching one number, they're growing forever. So we say does not exist due to unbounded growth. Right, either of those are good enough to make this top statement true, that the limit as x approaches 0 of f is not equal to f of 0. If something doesn't exist, then it can't be equal to something else. Okay, so we can kind of work around on the other side. So show that f is continuous at x equals 2. Maybe we'll make another sketch, see if I can get a better color. All right, maybe blue. So I'll just graph this. 2 is going to be right there. And obviously, visually, f is continuous at 2. And so what are we going to say? We're going to say basically, the limit as x approaches 2 from the left of f is equal to the limit as x approaches 2 from the right of f. And those y values are both approaching f of 2. Okay? So what are we going to say? So let's see. Limit as x approaches 2 from the left of f, what's that equal to? Well, that's equal to 1/2. And we're just going to pretend like we know that. We're not going to worry about a numeric limit. Choose another color. Let's see, green. And then the limit as x approaches 2 on the right of f of x, well, that's 1/2 as well. And then we need one more thing in the middle to match everything up. Let's choose yellow. And what are those equal to? Those are both equal to f of 2. What would we get if we substituted 2 into f? Well, we'd get 1/2. And so we can conclude, so f is continuous at x equals 2. And I'm realizing I don't think I had a conclusion on the last page. So I had that the limit as x approaches 0 of f is not equal to f of 0. And then I gave some reasons why, but I never concluded. So f is not continuous at x equals 0. And you might think, hey, that's pretty obvious that that's what we were answering, but, well, if you didn't write it down, we assume you don't know that. Okay. If you were in class, we'd talk about, hey, what this definition means, but you kind of think to that yourself, and let's go on. So now we have to worry about checking continuity on something that may or may not be continuous at x equals 3. And how do we think of piecewise defined functions? Well, really, you have one rule. You're going to use the square root of x plus 1 if x is 0 or 1 or 2, 1/2, really anything between 0 and 3. And, if your x value is 3.1 or 4 or 4.9, something like that, you're going to use 5 minus x. And let's just do this algebraically before we worry about the sketch, or maybe this would help us make a sketch. So let's see, how do I want to start? I want to start with if g of x is continuous at x equals 3, and then whenever I see a question like this, I'm always thinking the formal definition of continuity. That would mean the limit as x approaches 3 from the left of g of x should be equal to g of 3, should be equal to the limit as x approaches 3 on the right of g of x. So let's see. If I use numbers like 2.9, 2.99, 2.999, limit as x approaches 3 on the left, those all fit in this hey 0 to 3 stuff. So really, I'm going to be substituting numbers closer and closer to 3 into the square root of x plus 1. So maybe I'll write it that way, the square root of 3 plus 1. And what would I use for g of 3 itself? Well, where's my little eraser? G of 3 itself, we have that less than or equal to, so that's also the square root of 3 plus 1, because I would just be literally putting 3 into that square root of x plus 1. And let's see. If I do 3.1, 3.01, 3.001, I'm talking about over here, so that would be 5 minus numbers closer and closer to 3. And let's see, what am I going to do next? I'm just going to rewrite this so I can combine everything. Instead of having a 3-piece, now I have 1 left, 1 right. And so the square root of 3 plus 1 is 2. 5 minus 2 is 3. And so we got something that was true. We didn't get like 2 equals 4. We got 2 equals 2. And so we know, hey, we said if g is continuous at 3, this statement would be true. And since we got a true statement, g is continuous at x equals 3. All right, so a big part of calculus is going to be removing discontinuities with derivatives later on, kind of resolving instantaneous rate of change. And so we might need to make a function continuous at a point. And so notice, well, we have this k to fill in, and sometimes you'd be given a number instead of a k, and you have to just kind of rearrange. So maybe, I think I'm going to start off, I'm assuming f is not continuous at 1, or maybe, let me say that another way. I'm assuming if I substitute 1 into this denominator, I'm going to get 0. So let's see. I'm thinking 1 squared minus 4 plus 3. Yep, that's indeed 0. So let's factor out this piece. And remember, we have to have our whole f here. So let's see, x, and that's going to be x minus 1, x minus 2 as factors, over x minus 1, x minus 3 as factors. When x is not equal to 1, when x is equal to 1, we use k. We want to rewrite all of that. And so let's do what we previously did. If f is continuous at x equals 1, and I'm going to use that two-sided limit, because I know, I'll show you what I mean here in a second. The limit as x approaches 1 of both sides of f should be equal to f of 1. I know if I use 0.9, 1.1, 0.99, 1.01, I'm always going to be using this same piece. And so I might as well do a two-sided limit. Okay, so let's deal with the right-hand side first. So f of 1, that's this bottom part. That's k. Right? That says, hey, when x is 1, you use k. On the other side, the limit as x approaches 1 of f. Maybe we make that a little more comprehensible and use a bigger structure. Limit as x approaches 1 of x minus 1 multiplied by x minus 2 over x minus 1 times x minus 3. And then we get to thinking, well, what would happen if I use 1.1? What would happen if I use 0.99? And I guess what's going on in my head, I'll draw it over here. If I use 1.1 minus 1, and then 1.1 minus 2, 1.1 minus 1, 1.1 minus 3, well, these two over here are going to divide to be 1. And that's going to be true almost no matter what I use. Well, almost. If I use 0.9 minus 1, 0.9 minus 2, 0.9 minus 1, 0.9 minus 3, again, I get, well, those things over here, what came out of the x minus 1s divide to be 1. And so I might as well not even use that. I'm going to go ahead and rewrite. I'm not going to cross them out because they still exist, but what I know is I would get the exact same limit just ignoring those x minus 1s. So I'll say, hey, the limit as x approaches 1 of x minus 2 over x minus 3 is equal to k, because now, this thing is continuous. Okay? And so now I know, hey, I can just substitute in 1 minus 2 over 1 minus 3 is equal to k. And then I'm out of room, darn it. I want to have it on the same page. So let's see, that's negative 1 over negative 2. 1/2 is equal to k. All right, that's all I have.